Problem, we're considering coffee filters falling through the air at terminal speed. And in the problem statement, we're given a set of data. So what we do first is that we'll take this data. So the data is terminal velocity versus resistive force. So we square all the velocities in the data, then take the resistive force. So you have terminal velocity squared on this column and resistive force on this other column. And we go to Excel and we take this data and we plot the data. So if we plot the data, we have something like this. On the x-axis, we have terminal velocity squared. On the y-axis, we have resistive force. And using Excel's linear regression function, we do a linear fit on this data, and then we find that Excel can give us a best fit. So this best fit we see is here. It's r equals the slope times x, where x is terminal velocity squared, and we find the slope through Excel to just be 0.0162 kilograms per meter. So for this, we also say that resistive force has this form, proportional to terminal velocity squared. And theoretically, if you check your textbook, you'll see that we expect the resistive force to have this form. So making these two equal to each other, we find that 1/2 d rho times the area is equal to the slope. So now we set the density of the coffee filters to be 1.2 kilograms per meter cube, and we model them as circles with radius 10.5 centimeters. So if that's the radius, they have that their area is going to be 0.035 meters squared. So we can plug those in, and in this we can solve for the value of d. Solve for the value of d, we obtain this. We obtain 0.0778. So next, what we're going to do is we're going to take the 8 point on the graph. The 8 point on the graph is somewhere around here. This is, so you see it's not exactly on the line of our best fit. So we use the equation of our fit to obtain a very slightly different value of the resistive force. So we have R, which is what we measure, 0.128 newtons. And we look at the prediction of our fit, it is slightly different, is 0.127008 newtons. We call that error F because it comes from the fit. So we calculate the percent difference between these two quantities using this formula. It's a very standard error analysis, and we find the percent difference between these two values to be just 1.5%. So they're pretty close to each other. It's like the fit is not too bad. So in all of these, what can we comment? So is it doing this analysis of this data on falling coffee filters? Well, first we confirm the theory in that the resistive force goes like the square of the velocity. Uncertainty is low, so it is going to be more than 1.5% because you see there are points that are further away from the fit line than just the 8 point, but they're not that much further away. So we'll say that the furthest point away is going to be around 2% difference between the two. And finally, we also found our drag coefficient to be 0.0778, and this comes with an error of just 2%, which is just the error on the value of the slope compared to the data.